Is Wednesday, 20th of November 2024. We'll look around from linear algebra subspace to eigenspace. Let's go ahead. Let's say given V1, V2, and in a vector space V, H is subspace spanned by V1 and V2. We will show that H is a subspace of V. And what we should show is first, H should have zero vector. And second, H should be closed under vector addition. And H should be closed under scalar multiplication. If we put 0 on vector element, then it becomes 0. And if we put each vector, and if we make linear combination, if we plus each other, then it is also can be represented as the span of its vector of what H has. So it will be closed under the vector addition. And also, if we multiply one of the vector, we will fix the vector, and if we multiply it, we can also represent it as the scalar multiplication of its vector element in the vector space. So we can prove that H is a subspace of V. And there's some proposition regarding matrix. I will read it. First, column space of n by n. We will think about column space of n by n. Columns and n by n matrix is all of Rn. If and only if equation Ax equals b has solution for each b in Rn. It is equivalent with for every b in Rn, Ax equals b has a solution. And it's also equivalent with for every b in Rn, b can be expressed as linear combination column of A. And also it's equivalent to with the column space is Rn, and let A be n by n matrix, then from 1 to 5 is equivalent as when it is linearly independent and invertible. First, the column sub A from a basis of Rn, and dimension of column A will be n, and rank of A will be n, and null space of A will be only 0, and dimension of null space A will be 0. And someone confused between kernel and image. Kernel is subspace of V, and image is subspace of W. So what makes image 0 is element of kernel. Okay. Now let's see what is similarity. If in n by n matrix, if the n by n matrix A and B are similar, then they have same eigenvalue because they have same characteristic polynomial. Matrices are not similar even though they have same eigenvalue. So when they have same eigenvalue, then they have same characteristic polynomial. And when they are similar, then they have same eigenvalue and they have same characteristic polynomial is true. Vice versa is not true. It is related with diagonalization, which is we can factorize A equals to P dP minus 1. If I read the proof, if B is P minus 1 AP, then B minus lambda I can be represented as P minus AP minus lambda P minus 1P. So it can be factorized as P minus 1 A minus lambda AP. Then determinant B A minus lambda I, if we factorize this, then it will be same with determinant P minus 1 determinant A minus lambda I multiply determinant P, which we use determinant property, which is determinant AB is equal with determinant A multiplied determinant B. And when if A and B are M by M matrix, then A is similar to B. If there is an invertible matrix P such that P minus 1 AP equals to B, which is equal to A equals to PBP minus 1. And we will say when A goes to P minus 1, A, P, we will call this as similarity transformation. Oh. When we do diagonalization, then it will be A equals to PDP minus 1. We can do sanitary check by AP equals to A. AP is A and with vectors, and PD will be with eigenvalues. So we can do sanitary check by check each of AV1, check each of AP is PD, the element of AP and PD. And when you do factorization, you can easily do by solve determinant A minus lambda equals to 0, and you can find eigenvalue and which will construct matrix D. And by that, you can find linearly independent eigenvectors or basis of eigenspace. You can construct matrix P, and you can make PDP minus some matrix. And if there are n list of eigenvalue, then there is n independent eigenvalue exist, which is same with P is invertible matrix and A is diagonalizable. If we think there's no n list of distinct eigenvalues, which means there's no n independent vector, then we can't make P inverse, so we can factorize it as PDP minus 1 inverse. So, which is very natural. If we can make P, then we can't make P minus 1, then it will be not diagonalizable. So if there are n list of eigenvalue, then there will be n independent eigenvector exist, and it will be equivalent with P is invertible matrix, and A is diagonalizable. Thank you so much.